Again, welcome to lecture number 9. Again, this is our lecture number 9. In this lecture, we are going to discuss about applications of derivatives. Here we're going to talk about marginals and also derivatives. This is the last section of chapter 9 of our course textbook. So in chapter 9, we have sections from 1 to 9. So I name it the sessions by lectures. This is lecture number 9. So next lecture will be 10-1, which is chapter 10, lecture 1. So again, this is our last lecture in chapter 9. We are going to focus on applications of derivatives. So our main objective is how to find the marginal cost, also marginal revenue at different levels of production. Anytime we are looking for marginal cost or marginal revenue, it means we have to look for the derivative of the function, and that will give us the marginal cost or revenue function. Then at any number of units or products, we are going to find the marginal cost or the revenue of it. And the concept of a marginal revenue, for example, if we have a question saying that, okay, we should find the marginal revenue when the X number of units is 20. Let's say the company produced 20 items. This means the result we get for the marginal revenue at 20 items means the revenue we are going to gain when we produce the 21st item. That's from 20 to 21 items. Same thing applied to the marginal cost or the marginal profit. If I'm looking for marginal cost after a company produced 32 items, it means the answer I will get will be the cost for 33rd item, the next item. So let's start with the marginal revenue. So we say the instantaneous rate of change. We know previous lectures, we said instantaneous rate of change is the derivative of that very function. So here we are talking about marginal revenue. So instantaneous rate of change, that's the derivative of the revenue function, gives us the marginal revenue function. So anytime we have a question and a function is given and they say we should find the marginal revenue of the function, basically it means finding the instantaneous rate of change, which is the derivative of the function. So here we say if R equal to R at X, R represents the revenue, X is the number of products, is the total revenue function for a commodity, X will be the number of commodity. Then the marginal revenue function, which is MR, is the derivative of the function. Very straightforward. Here we should note that if the demand function for a product in a monopoly market is P equal to F at X, then the total revenue from the sale of X units will be P times X, which will be F at X times X. Again, this is the total revenue from the sale of X unit, total revenue. Now, if we're going to find the marginal revenue from the sale of X units, then we have to find the derivative of the function R at X, which will be the derivative of P. If P is a function F at X, then we find the derivative of F at X times the X unit. So let's see an example, our example 1. Here they said if the demand for a product in a monopoly market is given by P equal to 16 minus 0.02x. So this is our function. That is the demand for a product, P equal to 16 minus 0.02x, where X is the number of units and P is the price per unit. We should find the total revenue function and also find the marginal revenue for this product at X equal to 40. Now, you remember the P, they said is the price. So to find the revenue, it will be what? The price times X. X will be the number of units sold. So if the number of units sold is 100 and the price is $2, then the total revenue will be 200, 2 times 100. So let's see the solution. That will be our first solution. Total revenue will be P times X, because S is the number of units. P is the price per unit, so P times X. Now, to find the marginal revenue, then we have to find the derivative of the revenue function, which will be P is 16 minus 0.02x. So multiply by x, we get 16x minus 0.02x squared. That will be the A answer, the revenue function. Then we take the derivative of the function, and that's to be for B. Then we find the function value when x equal to 40. So A, the total revenue function is what? R at x equal to Px, because P is the price, as they said, and also S is the number of units. And P is given to us to be 16 minus 0.02x. So we multiply by x, which is the number of units. So our final function, total revenue function, will be 16x minus 0.02x squared. That's for A. Now we go to B. In B, they say we should find the marginal revenue function, which will be again derivative of the function. In this case, the derivative of the revenue function. And this will give us 16 minus 0.04x. We know the rules already. I have 16x. So x raised to the power 1. 1 times 16 is 16. 1 minus 1 is 0. Any base raised to the exponent 0 is 1. So the derivative of 16x will be 16. Now 0.02x squared. 2 times 0.02 will give me 0.04. 2 minus 1 for the exponent will be 1, so it's x. So this is our, again, derivative of revenue function, R at x, which also is called the marginal revenue. Now, the question said we should find the revenue when what? X equal to 40, which means the company produced 40 items. But if I use the total revenue function for 40, it means the revenue when the company produced 40 items. But marginal revenue means the revenue when the company produced from 40 to 41st to 41. Not all the 40, but so after we produce 40, what revenue we're going to get when we produce one more item is what marginal revenue means, from 40 to 41, additional one item. So at S equal to 40, we substitute 40, then we get 16 minus 0.04 times 40. That gives us 16 minus 1.6. 0.04 times 40 will give me 1.6. So the difference will be 14.4. So that's why you can see the answer we write here. We say $14.40 per what? Per unit. So the 40 doesn't mean that we are producing the revenue we get to produce the 40 items. It means after we produce 40 items, the next item, the revenue of it will be $14.40 per unit. But if I'm looking for the total revenue for all the 40 items, then I'll use the total revenue function. Okay, so next we say the marginal revenue is an approximation or estimate of a revenue gain from the sale of one additional unit. As I said earlier, it's not the 40 units together. If it's 40 units, we use the total revenue function. If we use the marginal revenue function, it means if it's at 40, what will be the additional revenue after 40, the next item, which is 41. So we have used marginal revenue in example 1 to find that the revenue from the sale of 41st item will be $14.40. So the actual increase in revenue from the sale of 47 items is this. Now, what we are doing here is that instead of using the marginal revenue function, we use the total function to find the 41 items, what will be the total revenue. The 40 items, what will be the total revenue. Then find the difference. You'll see that we almost get the same answer, 14.38. Here is 14.40. So this method means we are not using the derivative of the R function, revenue function, or the marginal revenue. We are not using it. We are using the total revenue function. So we know if it's at 40 marginal revenue, it means After 40, the next item that will be produced, the revenue of it. So it will be 41st. And the difference with 40 items, revenue at 41st, revenue at 40, the difference it gives us. So marginal revenue and other marginals can be used to predict for more than one additional unit. And that's the whole concept here. For instance, in example 1, the marginal revenue for 40 is $14.40 per unit. It means that the expected or approximate revenue for the 41st through the 45th item sold will be 5 times 14.4072. This is for the next 5 items after 40. So it will be 5 times 14.40, which will give us 72. And the actual revenue for these 5 items is, now we are finding the difference between 45 items and 40. So 45 minus 40 at revenue, and that gives me $71.50. We can see that it's almost close to using the marginal revenue function, which is the derivative, $72. Here we get, if we use the actual total revenue function, we get 71.50. Okay, so let's move to marginal cost. The concept of marginal revenue is the same as marginal cost. Here also is that we want to find the cost of additional product that was produced. What will be the cost? Same as saying what will be the total revenue or even the profit of additional cost if we sell it. So the derivative of a total cost function gives again the marginal cost revenue. So it's the same concept. As we said, the derivative of a what? A total revenue function gives us the marginal revenue function. Same thing, the derivative of a total cost function gives the marginal cost function. So here we represent C as the cost. So we say C, if C equal to C at X and is the total cost function for a commodity, then its derivative will be the marginal cost function, which is C derivative at X is the marginal cost function. So let's see an example. Suppose the daily cost in dollars for a certain factory to produce S kitchen blenders is given as following. So this is the cost function, the total cost function. A, find the marginal cost function for these blenders. Then B, find and interpret the marginal cost when X equal to 80 and also when S equal to 200. So when S equal to 80 means what will be the marginal cost when we produce the 81st item. Also, when S equal to 200, the same thing. What will be the marginal cost when we produce the next 201 item? Same concept as revenue. What will be the revenue when we again sell the 41st item or in a position? So let's do the first thing. We all know the derivative we completed with the derivative rules, regulations. So let's look at this function. We have the power rule here. It will be 3 times 0.001. So that will give me 0.003 x squared, because 3 minus 1. Minus 2 times 0.3, that will give me 0.6 x. 2 minus 1, so 0.6 x. And this will give me 32. And then we know the derivative of a constant value is 0. So let's look at the solution. We get 0.003 x squared, because 3 times 0.001 and 3 minus 1 x squared. 0.3 times 2, so we get 0.6. The exponent is 2 minus 1, so it will be x. Then the derivative of 32x will give me 32y, because we have exponent 1. 1 minus 1 is 0. Any term or any base raised to the power 0 is 1. And 1 times 32 is 32, so we have 32. And we again said that the derivative of a constant value is always 0. So this will be our solution for A. Now B, we are looking for the marginal cost when S equal to 80. So we'll substitute 80 for the X and solve the marginal cost. The same thing for 200, we do the same thing. Then they say we should interpret the result. What the result will mean is that, and the first one, when S equal to 80, we will say that the marginal cost for the 81st item is what we get. and 200 first item is what we get when S equal to 200. So we do the first one, substitute 80, we solve the equation, and we get 3.2. So it will be $3.20 per unit. Then we solve for the 200. We substitute 200 for X, we get $32 per unit. Now they say we should interpret the result. So these values for the marginal cost can be used to estimate the amount that total cost will be changed if the production were increased by one blender. So we can see how the total cost changes. From 80 to 100, we see the difference. And the first one, 3.2, means the total cost increased by $3.20 if the 81st blender were produced. And the same thing applied to the 200 also. 200 means 32 means that the total cost will increase by $32 if 200 first blender were produced. And before the previous example, instead of using the marginal revenue function, we can use the actual total cost function. So find at 81 and 80, find the difference, we can see it's closer. The same thing with the 200. Find out 200 and 201, the difference, we will see that to be close to 32. So because producing more units can never reduce the total cost of production, the following properties are valid for total cost function. So the more units we produce, because the thing is that we know in a company, we always have two types of costs, the fixed cost and also the variable cost. Fixed cost means whether we produce 0 units or 1,000 units, we are going to get that cost. For example, the rent or the leasing of the property. Now, variable cost means maybe the materials we are going to use. The more products we produce, the more materials we are going to use. So that's the concept here, is that producing more units can never reduce the total cost. So here we say the total cost can never be negative. If they are fixed costs, the cost of producing 0 unit is positive. For example, leasing a machine or property. Now the total cost function is always increasing because what? The more unit produced, the higher the total cost because we're going to use more materials. And there may be limitation on the unit produced, such as those imposed by the plant space. And this is again depends on the company capacity production. Okay, the last section is the marginal profit. Same concept, revenue, cost, profit. Marginal profit means we find the derivative of the profit function. That's it. But we should know one thing here. What is the formula for revenue? It will always be the price of a unit times the total price. What is the profit? Profit will always be what? Revenue minus what? Total cost. So as with marginal cost and marginal revenue, the derivative of a profit function for a commodity will give us the marginal profit function for the commodity. So marginal profit, let's see here we are assuming P is the profit equal to P at X is the profit function for a commodity. Then the marginal profit, of course, will be the derivative of P, same as we did for revenue and the cost. So the price of a product is determined in the market by the intersection of the market demand curve and also supply curve. This is the supply and demand. And as we said earlier, revenue formula is always the price times the number of units. A firm in a competitive market must sell its product for $200 per unit. The cost per unit per month is 80 plus X, where X represents the number of units sold. Now they say we should find the marginal profit function. So we know the profit is what? Total revenue minus total cost. So when I look at this question, they say a firm in a competitive market must sell its product for 200. Let's see, 200 per unit. So this means the revenue will be 200 times X, the number of units. Now the total cost per month is 80 plus X. where X represents. So profit will be 200 times X minus 80 plus X, because profit always will be the revenue minus the total cost. Revenue will be the price of an item times the number of items. So 200 times X. They give us the cost function to be 80 plus X, so minus 80 plus X. Then here, when we get the function, then we find the derivative of the function, and that will give us the marginal profit function. So let's see the solution. If the cost per unit is 80 plus X, then the total cost of S unit is given by the equation C at S will be what? 80 plus S times X. That is the total cost. Now, the same thing with the revenue. As I said, if the revenue per unit is 200, so the total revenue will be what? 200X. So the function given here, 80 plus S, is the total cost per unit. See, it's written here. So the total cost for the whole unit will be 80 plus S times X. I was giving an example that, for example, if the total cost for the whole system is 80 plus S, then I'll use this. But here they say the total cost per unit per X. So we multiply 80 plus S as one cost of a product times S, the number of products. So now we know the profit. It will be what? 200X, which is the revenue, minus 80S plus S squared. Then we find the derivative of it. So profit will be revenue X minus C X cos X. We substitute the value 200X minus 80S plus S squared. We open the parentheses, solve it, we get 120, because 80 minus 200 will give me 120. Minus and positive will give me minus, so I get S squared. So now we find the derivative of this function, which will give us 120 minus 2x. And that's it. Here we see the figure here shows the graph of a company total revenue and the total cost. When we plot the revenue and the total cost, this is what we get. And the intersection is where, again, the number of items, I'll use the term break even. Intersection means where there's no loss and no gain. So if 100 units are being produced and sold, we produce 101st item, increase or decrease the profit. If 300 units are being produced and sold, we produce 301st item, either increase or decrease the profit. If 1,000 are being produced, this is the same example as previous question. So here, if I want to solve this problem, I just have to plug 100 into the derivative of the function, the marginal, again, profit. And the answer I get means what? Same as what we did in revenue and also the cost. It means that the profit I will get when I produce the next item, which will be 101st. If it's 300, substitute 300 in the marginal profit function. And the answer you get means when I produce my 301st item, that will be the profit I will get. And the same thing applies to 1,000 units. We substitute 1,000 units in the marginal profit function, the X. The answer we get means when I produce 1,001, that will be the solution. So at a given S value, the slope of a tangent line to each function gives the marginal at that X value. So let's do the first one. We already explained it, but S equal to 100. We can see that the graph of R will be steeper than graph of C at X. Here we can see the value here. This is the number of units. So 100 is somewhere here. So we can see that R at X is steeper than, then that's the tangent line to R at X will be steeper than the tangent line. Hence, marginal revenue 100 should be greater than the marginal cost 100, which means that the revenue from one of us will exceed the cost. We can see from this function. So for example, if I produce, let's say 600 items, what happens? This is my cost. This is my revenue. So my revenue go up. But if I produce only 100 items, what happens? My revenue is less than my cost. So producing 100 items, I'm going to lose money. That's why I said the intersection of this point, which will be somewhere around 150 or 170 products, will give us what we call the break-even point, where there will be no loss, there will be no profit. Then from here going, we have profit now. We can see the marginal revenue and then the cost down. And that's what we meant by everything, the steepness, etc. Therefore, profit will increase when one of first item is produced. At S equal to 300 also, we look at the function, whether it's good, the revenue will increase also. At 1,000, of course, that also increased the cost. Let's look at they say to decrease. Let's look. Again, everything is based on the function. Everything is based on the function. So when I produce 1,000 products, again, we didn't get the functions through, but I can see that again, the revenue go up and the cost is down. But we can see that as this look like it's a parabola, and we'll reach some units that again, the cost will be going high and the revenue will go down. Unless that's where we have to have our capacity level. So that will be the conclusion of this lecture. In this lecture, we cover the applications of derivative using marginal. This is a business calculus class, so we talk about the marginal revenue, marginal cost, and also marginal profit. And we saw the both revenue, cost, and profit functions. So again, thank you for these lectures. Again, you can comment on my video or like it, and also you can subscribe it. Thank you.